Today we're going to look at section 5.4, eigenvectors and linear transformations. But before we get into that stuff, let's remember a few things from some previous ideas. So just recall that if I have a linear transformation, t, from Rn to Rn, actually they can be different, Rn to Rm, then remember that it has a matrix, A. It has a matrix. If it's from Rn to Rm, that means that the input vector is in Rn. So we're starting with a vector in Rn, which means I have to have n columns, so and m rows. So this is going to be an m by n matrix. And remember that T is the matrix that we get by, or A is the matrix that we get by taking the standard basis vectors in Rn and applying T to each of those, and then creating, so E1, E2, all the way to En, and then creating a matrix out of these things. So this is back from some previous chapters. But this is how we create the matrix corresponding to a given linear transformation. So that's the first thing. Now, we need to move to a bit more of an abstract setting. And rather than saying that we have a Rn to Rm, suppose that we have a linear transformation T from one vector space to another vector space, from V to W. Now remember that in order to talk about this in terms of matrices, we need to start with a basis for each of these things. So let's say that B is a basis for V, and C is a basis for W. And once we do that, really, remember that if I have a basis for V, that's a linearly independent spanning set, but once we have a basis, each vector in X has a corresponding set of coordinates. So remember, so that for X in V, I can write the coordinates of X relative to the basis B. And this is just an element of Rn, where n is the dimension of V. This is just a list of numbers. It's the scaling factor on each of the basis elements in the basis of V. And for some y in W, we can think about the coordinates of y relative to the basis C. So in doing so, this is a vector in Rn, where n is the dimension of V, and this is a vector in Rm, where n is the dimension of W. And then we can think about a matrix. Right? So what is, our question then is, what is the matrix for T? But in this case, this is not a matrix that depends just on the linear transformation. It depends on the choice of basis, B and C. So the matrix for T relative to B and C. But in terms of our idea from before, we've already, by looking at coordinates relative to a basis, we've put ourselves into Rn and Rm. And what that means is that it's exactly the same thing as we wrote before. A is just going to be the matrix that we get by applying T to each of the corresponding basis elements. B1 all the way to T of Bn, where the basis B is the vectors B1, B2, all the way to Bn. Okay, so let's see how that works in practice. We'll take a small step towards practicality here. It still feel a little bit abstract, but suppose that V is a vector space with basis B equal B1, B2, B3. Suppose W is a vector space with a basis C, C1, C2. suppose T is a linear transformation from V to W, and T of B1 is 2C1 minus C2. And so once I put B1 into T, then I end up over in W, and anything in W is a linear combination of C1 and C2. T of B2 is 3C1 plus C2, and T of B3 is 2C2. Our question is, what is the matrix for T relative to B and C? But that's exactly what we're talking about right up here. Okay, so T of B1 is a vector that's over in C2, but really what I'm looking at is, so what we've got is that since T of B1 is 2C1 minus C2, we're going to convert this, we're going to actually look at its coordinates relative to the basis C. And the coordinates of this relative to the basis C are just the coefficients of C1 and C2, since the C is just C1 and C2. So this is the vector 2 minus 1. T of B2 relative to the basis C is 3, 1. And T of B3 relative to the basis C is, since it's just 2C2, I get 0, 2. So if I put these into a matrix A is 2 minus 1, 3, 1, 0, 2. All right, now, suppose that T is a linear transformation from V to V. It's from a vector space to the same vector space. Suppose that a basis for the vector space B for the vector space V is B1, B2, B3. Suppose that V of B1 is now, since I'm going from V to V, we could have two things happen, right? So let's suppose that we have B, which is one basis for V, and we have another basis for the same vector space V. So since this is three-dimensional, I'd have to have three basis elements and a different basis C as well. So let's find the matrix A relative to the bases B and C if T of B1 is 3C1 minus C3, T of B2 is C2 plus 2C3, and T of B3 is C1 plus C2 minus C3. Again, this is not much different than the one we just looked at before. The only difference is that we're moving from a single vector space to itself using two separate bases for that same vector space. Now, working out the answer is the same. Since T of B1 is 3C1 minus C3, really we're looking at the coordinates of T of B1 relative to C, and we get 3, 0, minus 1. We need the coordinates of T of B2 relative to C, and we get 0, 1, 2. And finally, for the third one, we get the coordinates of T of B3 relative to C, and we get 1, 1, minus 1. which means our matrix A is just 3, 0, minus 1, 0, 1, 2, 1, 1, minus 1. Now, what does that really mean? This really gives us a map. Let's think about what this is, right? So if I multiply by a vector x, in terms of what we've got, this is a map that gets us from the vector space V to the vector space V, but we started with a vector that were in coordinates relative to B, and we end with a vector that's in coordinates relative to C. So this is really our change of coordinates matrix that we've already talked about. So this is a matrix that changes your coordinates from basis B to the basis C. So this is really the matrix A, which converts the basis B to our basis C. So remember what we actually looked at. We looked at something like this, where we had a matrix basis B converted to basis C, because when we multiply by a vector, we multiply by a vector with coordinates in basis B, and we end with a vector that gives us coordinates in the basis C. Now, the reason that this is helpful, and the reason that we're thinking about this now in terms of eigenvectors and eigenvalues and diagonal matrices, is the following. Right, so let's just remember. So suppose that I just have the matrix D, which is 2, 0, 0, 5. This is a diagonal matrix. Right, so what does this do? Let's think about this as this is a map D. It really is a linear transformation if we think about matrix multiplication from R2 to R2, because it's a 2 by 2 matrix. Right, so what happens to, let's say what happens to the unit, a square. Right, so what happens to all of these things that are right here? So this is in R2. I want to say what happens to this as I move under the linear transformation T. Diagonal matrices are nice, because what does this really mean? This is, remember that this first vector here is T of E1. So E1 gets sent to 2, 0. So E1 gets now sent to 2, 0, rather than just 1, 0. So this vector, if this is just 1, gets sent to the vector which is twice as long. The second vector gets sent to a vector which is now 5 times as long. So T of E2 is 5, 0. So this square becomes a rectangle. But that's about as nice as things could get. Because if we looked at a general matrix, we're going to find that this square is going to become some pushed over parallelogram. Right? So what's nice about diagonal matrices is that it takes squares to rectangles, and we don't end up getting any parallelograms, which can complicate our stuff. So in general, if we had a more general matrix, which was not diagonal, we might find something where a square gets sent to it could just even be a diamond shape like this, some funny looking parallelogram, and diagonal matrices are much nicer in that regard. And so what we might ask in this situation is for the following. Let's start with the matrix A, 1, 2, 3, minus 4. Let's think about a linear transformation T from R2 to R2, given by T of X is AX, just multiplication by A, our favorite. And our question might be the following. Find a basis for R2, for which the matrix for T relative to that basis. Right? So the matrix for T relative to the basis is diagonal. because diagonal matrices are nice. They're nice to work with. We're looking to change our basis here so that multiplication by the matrix A corresponds to multiplication by a diagonal matrix. And the idea here is really all we're going to have to do is diagonalize this matrix, which comes from our last section. If A is P times D times P inverse, that is our diagonalization process. If I can do this, well, what does that mean? Right, so that means that first of all, what does this PDP inverse actually do for us? Let's think about that. Since under our diagonalization procedure, remember that P is created by finding the eigenvectors. D is created by finding the eigenvalues. But if I have any matrix P, right? So P is an invertible matrix because it's linearly independent eigenvectors. Okay, so in this case, what that means is that since P is a matrix created out of linearly independent eigenvectors, P is invertible. Right, the column vectors form a basis for R2. So P is, let's call P B1, B2, so that the basis B, B1, B2, is in fact a basis for R2. Is a basis for R2. Now, so what is this saying, right? So suppose that I had a vector in R2, and suppose that the coordinates of that vector, and suppose that we have that vector in terms of its coordinates relative to this basis. Right? So what this means is, so remember, what is a P of 1, 0? Well, that's going to be B1, B2 times 1, 0, which is just B1, because I take 1, B1, and 0, B2. So notice what this has done. Right, so how do I get B1 back? Well, B1 corresponds to 1, 0. So this is like 1 B1 plus 0 B2. So this I'm thinking about as coordinates in the basis B1, B2 in the basis B, and it outputs the actual vector B1. So this is saying that P is actually the change of coordinates from the basis B to the standard basis, E1, E2. So in other words, P of a vector x written in its coordinates relative to the basis B is in fact just x, right? Because what is this saying? If I take a vector x and I look at its coordinates relative to B, and then I apply P, but P is the change of coordinates from B to the standard basis. So if I have the coordinates in basis B, and then I multiply by the matrix P, well then I get its coordinates in the standard basis, which is just x. And so this also tells us that XB is P inverse X. So these are things that we saw before from back in chapter 4 when we talked about change of coordinates. All right, now we've got to put that all together and remember what our goal was. Our goal was to say how can I find a basis for which the matrix A corresponded to a diagonal matrix under that new basis. Now, our idea was to say to diagonalize the matrix. If A is P, D, P inverse, well, what does that mean? All right, so that means that let's say, what is the matrix? So and the basis B is B1, B2, where P is B1, B2, as before. Then the matrix for the linear transformation T relative to the basis B. Well, that's given by T of B1 in the coordinate system B. This is what we talked about before. So the T of B1 relative to the basis B, T of B2 relative to the basis B. But T of B1, remember T is just multiplication by A, so this is A B1 relative to the basis B, and then A B2 relative to the basis B. Okay, but according to what we just discovered, that when I say relative to the basis B, this is the same thing as saying P inverse, because I'm changing my coordinates, P inverse times AB. If I want to move over to the basis B, I have to multiply by P inverse. So this is P inverse A, B1. This is P inverse A, B2. But P inverse A, since A was P, D, P inverse, but P inverse, so this is just a matrix. Let's just write it like this. This is P inverse times A times B1, B2, because a matrix, this is just a matrix multiplied by another matrix. So we can really think about factoring that out. But B1, B2 is just the matrix P. And remember what we started with way back when. What we started with was the matrix for T relative to the basis B. But A is P inverse. A was P, D, P inverse. P inverse P's cancel, P inverse P's cancel, and we get D back. So the matrix for T relative to the basis B is just this middle diagonal D if we can diagonalize our matrix. And so for this particular problem, we've gone far away from where we started. Let's just remember where we began. We began with the matrix 1, 2, 3, minus 4. So A was 1, 2, 3, minus 4. We wanted to find a basis under which A corresponded to multiplying by a diagonal matrix, which means we need to diagonalize this matrix. So now we will diagonalize. And we do that first by finding eigenvalues. And we find eigenvalues. Let's practice this whole process. We look at A minus lambda I and take its determinant. So that's the determinant of 1 minus lambda, 2, 3, minus 4 minus lambda, which is 1 minus lambda minus 4 minus lambda minus 6, which is negative 4. That's minus lambda plus 4 lambda, which is plus 3 lambda, plus lambda squared, minus 6. That's lambda squared plus 3 lambda minus 10, which becomes lambda plus 5 lambda minus 2. And so that tells us that our eigenvalues are minus 5 and 2. And now we have to go through the whole process of finding the eigenvectors. If we look at lambda equal 2, then A minus 2i is minus 1, 2. We're taking 2 off on the diagonal, and 3 minus 6. This row is just a multiple of the first, so this row reduces to 1 a minus 1, well, 1, negative 2, 0, 0. Which tells me that x1 is 2x2 and x2 is 3. So I get 2, 1 as my eigenvector. So for lambda equal 2, our eigenvector was v1 is 2, 1. For lambda equal minus 5, we look at a minus 5i, which is add 5 on the diagonals, and we get 6, 2, 3, 1. Again, this is a multiple of this, and so this row reduces to, if I divide by 2, 3, 1, 0, 0. We could make this 1, 1/3, but fractions are not as nice when we're looking at vectors. So this says that 3x1 is minus x2 and x2 is 3. So our vector becomes, so this is x1. Well, we can write it like that. x1 is minus 1/3 x2, so minus 1/3, and x2 is 3, so we get 1. But if I multiply by 3, then I'm going to conclude that my second eigenvector is minus 1, 3. So now I've got my eigenvectors and my eigenvalues. And I can say that A is P, D, P inverse, where P is 2, 1, minus 1, 3, and D is 2, 1 corresponds to 2, so a diagonal matrix with 2 here, and minus 5 on the second one. And so the basis under which A corresponds to multiplication by a diagonal matrix is the basis given by the eigenvectors, 2, 1, minus 1, 3. And the diagonal matrix that this corresponds to is the diagonal matrix D, 2, 0, 0, minus 5. And that's what we need to talk about from 5.4. See you next time for 5.5, complex eigenvalues.